customer requires that we design an emergency brake that can be actuated both electronically and manually. The system is to function as a safety device which remains independent of the onboard computer, can be actuated electronically in the event of emergency, and retain manual functionality for passenger override.
Like all emergency brakes, our automated e-brake operates by pulling a cable connected to a lever on the rear brake caliper. A specialized cable connector bracket decouples the motion of a linear actuator from the emergency brake handle as it applies an expected 1800 newtons of tension into the e-brake cables. In the event of an electronic failure, the e-brake can still be applied manually without any loss of functionality. The same cable connector bracket again makes it possible to decouple the e-brake handle motion from the linear actuator.
Through QFD, we found what was most important to our 4 customers: GET, the senior project team, end user, and the manufacturer. It was found that the first 3 customers had a common ground with their top 3 concerns, which included having proper holding torque and a proper max tension in the brake cables. GT, though, was concerned with the simplicity of the design and included reducing the connectors used as one of their top 3 concerns. On the other hand, the senior project team and the end user cared about the actuation force being properly optimized. However, the manufacturer differs since they are obviously concerned with ease of assembly and included reducing amount of electrical components, connectors used, and volume under frame. After having followed the 8 steps of QFD, we could clearly see what we needed to focus on as a team.
Our ultimate revision met all the requirements set forth by the clients, while simultaneously overcoming the challenges of packaging due to the limited space available under the frame. This was accomplished by remote mounting the actuator and transferring motion by cables. The final design drastically simplified the manufacturing process compared to early concepts, in addition to reducing cost. As one can see, the linear actuator can effectively apply the requisite 1800 newtons of tension to the e-brake cables without the movement of other components. And as required by the customer, the brake can still be actuated manually via the e-brake handle without interference from the linear actuator.
FEA was conducted on each mounting bracket with an applied load of 2200 newtons to simulate a worst-case scenario from the actuator. Normalized 4140 steel was chosen for the brackets due to the large loading experienced. Each bracket required unique boundary conditions to ensure accurate results. A triangular mesh was used in each simulation, and fine mesh controls were applied to areas of interest, including contact areas, bolt holes, and fillets. Bolts were simulated using SOLIDWORKS Toolbox add-in. Von Mises stresses were then taken from each simulation and compared to the yield strength to give a factor of safety, as well as the SN curve to give fatigue life. All brackets met the required static loading safety factor of 2 and fatigue life of 30,000 cycles. The smallest safety factor for fatigue was found to be 1.4. All bolts also exceeded the required safety factor of 2. The cable-to-frame bracket was simulated by fixing the ends of the frame and applying the 2200 Newton load between the 2 holes for the cable housings. A fine mesh was applied to the contact areas and the edges of the frame member. A maximum stress of 297 MPa was seen at the edge of the frame, giving a safety factor of 2.1. The safety factor for the bolts was found to be 3.6, while the fatigue life was found to be 75,000 cycles.